Welcome back to the Deep Dive. Today, we're taking you on an incredible journey. Not outer space, but deep, deep inside our own planet.
Mhm.
We're going to unravel a mystery nearly 3,000 kilometers beneath our feet.
That's right.
We're talking about Earth's seismic D layer. And it seems scientists have, well, finally cracked this long-standing puzzle. It's baffled geophysicists for decades.
It really has.
So our mission for you today, give you the shortcut, the key insights on this amazing scientific breakthrough. We'll pull out what really matters from the research.
And it's such a crucial area to explore. You might picture the Earth's insides as like neat static layers.
Yeah, sort of like an onion.
Exactly. But the core mantle boundary, that's our focus today. It's anything but static, it's dynamic, it's restless,
Sure.
and it plays this surprisingly vital role in how our planet behaves. Influences everything, really. The ground, the magnetic field. It's a real frontier.
Okay, let's unpack this then, starting right at the beginning. The core mantle boundary, the CMB. Where exactly are we talking about? Give us the scale.
Okay. So the CMB isn't some, vague zone. It's a pretty precise boundary. We're talking 2,891 kilometers down.
That's nearly 1,800 miles.
Yep, right below the surface. And it's this fundamental divider. It separates the planet's solid silicate mantle
Solid rock.
from its liquid iron-nickel outer core. So, yeah, think solid rock meeting molten metal deep inside the Earth.
And obviously we can't just, drill down there. So how do we see it? What's our window into the deep Earth?
Well, that's where seismology is so powerful. We use seismic waves from earthquakes. Think of it like an ultrasound for the planet.
Okay.
So when P waves, those are the primary compressional waves. When they hit this boundary, boom, they suddenly slow way down in the outer core compared to the mantle
You just
above.
slow down.
Yeah, quite a bit. And even more telling, the S waves, the shear wave, they just disappear, vanish completely.
Why is that?
Because liquids can't support shear motion. So that sudden stop tells us definitively we've hit liquid. Solid meets molten, that's the boundary, often called the Gutenberg discontinuity.
Right, after the seismology. So it's not just a clean, smooth line down there then. Does it have, texture, a landscape even?
Oh, far from smooth. Seismic studies, tomography, they've shown the CMB is incredibly complex, almost like an upside-down mountain range in some ways.
Really?
Yeah, there's even evidence for a distinct layer right above the CMB. It might be made of this different mineral phase called post-perovskite.
Post-perovskite.
And yes, the imaging shows huge irregularities, massive structures, almost like blobs. We call them large, low shear velocity provinces, or LLSVPs.
LLSVPs.
Yeah, gee.
Yeah. There are two huge ones under Africa and the Pacific. Think of them like giant, hot, slow-moving piles of rock, sort of like continents, but deep inside, they really affect things.
So definitely not uniform, and I bet it's incredibly hot down there, too.
Oh, extremely hot. The very top of the outer core is thought to be maybe 500 to 1,800 Kelvin hotter than the mantle right above it.
That's a huge temperature jump. It is. It creates this critical thermal boundary layer. And yes, we think this boundary has topography, like mountains and valleys, supported by the slow turning, the convection in the solid mantle above.
Convection in solid rock.
Well, solid state convection, very slow movement over millions of years. And, these variations in temperature and shape at the CMB, they affect how the liquid iron flows in the outer core.
And that flow.
That's what generates Earth's magnetic field, our protective shield. So the landscape down there is directly linked to the shield protecting us up here.
That connection is just mind-blowing. It's not some dead layer. It's a living part of the planet's engine.
Okay, so within this complex CMB zone, there's a specific puzzle piece. The Dio region? What's that?
Right, the Dio. It's about a 200-kilometer thick slice of the lower mantle sitting directly on top of the CMB.
And the name Dio sounds a bit technical.
It is, a bit. Comes from a geophysicist, Keith Bullen. Back in the 40s, he labeled Earth's layers alphabetically. The whole lower mantle was just a D.
Simple enough. But then, around 1949, he realized D wasn't uniform. He split it. The upper part became D prime, and the bottom 200 kilometers right above the core, he called D double prime.
Like finding a sub-basement.
Exactly like that.
And this D layer, it has its own quirks too, I gather.
It certainly does. We know it's not perfectly spherical.
Yeah.
And the variations within it form structures, sort of like those LLSVPs, but maybe on a different scale, like core continents.
Core continents.
Yeah, and they seem to move over time. They might influence things like volcanic hotspots, think Hawaii, and the bigger mantle convection patterns. So there's this whole dynamic geography deep inside.
Okay, which brings us to the central mystery. the thing that stumped scientists, the D-layer anomaly. You said earthquake waves do something weird here. Counterintuitive. What happens?
That's the crux of it. Right around 2,700 kilometers depth, as seismic waves enter this DO region, they suddenly speed up.
Speed up.
Yeah.
That seems backwards.
Exactly. Usually, a speed change like that means you've hit a totally different type of material, something denser, maybe. But we thought we knew the minerals down there, so why the acceleration? It was a real seismic riddle for years.
Like hitting an invisible accelerator pedal.
Precisely. No obvious reason for it.
Okay, this is where it gets really interesting. Because this mystery, it seems, is solved. Tell us about the breakthrough. Who figured it out?
Yeah, the credit here goes to Professor Motohiko Murakami at ETH Zurich and his team. They finally put the pieces together, combining seismic data with some really innovative lab work.
And this wasn't overnight, right? This discovery has roots going back almost 2 decades, to 2004.
That's right. Back in 2004, Murakami made a really key finding. He discovered that perovskite, the main mineral in the lower mantle, actually transforms under the intense pressure and heat near the CMB. It changes into a new phase called post-perovskite.
Ah, the post-perovskite we mentioned earlier.
Exactly, and this new mineral phase is stable under those extreme conditions, so it becomes the dominant mineral down there in the dew layer.
So, okay, new mineral phase.
Oh.
Maybe that explains the speed change. Did they think they'd solved it then?
For a little while, yes. After 2004, the thinking was, okay, this phase changed from perovskite to post-perovskite. That must be it. That's why the waves speed up.
Right.
Makes sense, right?
Seems logical. Different mineral, different speed.
But science is rarely that simple.
Mm.
By 2007, Murakami and others realized, looking at more detailed seismic data, that the mineral change alone wasn't quite enough. It couldn't fully explain the exact amount of acceleration they were seeing.
So close, but not the whole picture.
Right. There was still something missing. The numbers didn't perfectly line up.
Okay, so if it's not just a different mineral, what else could be happening in solid rock? What was the final piece of the puzzle?
Well, this is where complex computer modeling came in, simulating how minerals behave under those insane pressures and temperatures. And the breakthrough was realizing that post-perovskite's properties, specifically its hardness,
Yeah.
it changes depending on the direction its crystals are pointing. It's anisotropic, basically.
So like wood grain.
Yeah.
Stronger in one direction than another.
That's a great analogy, exactly like that. And the model showed that the cause of the seismic acceleration happens when all those tiny post-perovskite crystals get pushed into alignment, all pointing the same way.
All lined up.
All lined up. And this alignment happens specifically at depths around 2,700 kilometers, right where the D anomaly starts.
Wow. So it's not just the mineral, it's how the mineral is arranged.
Precisely. Murakami himself said, "We have finally found the last piece of the puzzle." It's a really elegant solution, actually.
It really is. Solving something that puzzled people for generations. So how on earth do you test that? You can't exactly go down there and check the crystal alignment. The lab work must have been incredible.
Oh, absolutely. It was state-of-the-art stuff. They had to recreate DIA conditions in the lab. First, they needed a stand-in for post-perovskite, so they synthesized this material, MEbG03 orthopyroxene.
How do you make that?
Get this. They mixed fine powders of germanium oxide and magnesium oxide and cooked it in an electric furnace at 1,000 degrees Celsius for 104 hours.
Whoa, that's over 4 days straight, just baking minerals.
Pretty much. Then they take the synthetic stuff, this tiny sample, and they squeeze it between diamond anvils.
Diamond anvils?
Yep. Tiny, incredibly strong diamonds that create immense pressure, mimicking the deep earth. While it's squeezed, they blast it with a CO2 laser to heat it up to DO temperatures.
So extreme pressure, extreme heat.
Exactly. And while it's under those conditions, they measure how fast sound waves travel through it. That's the acoustic velocity. And they use X-rays to see the crystal structure, the diffraction patterns, lots of complex analysis.
And did it work? Did the lab results match the theory?
They did, beautifully. The team successfully recreated the conditions where you see that acceleration, that speed up of waves.
Amazing.
Their experiments clearly showed that heat and pressure combined can force those crystals to align in one direction. And when they align, boom, seismic waves travel faster through it, just like the anomaly observed in the Earth.
So what's really fascinating here, then, is that the anomaly isn't because the stuff changes,
Right.
but because of how the stuff behaves. A change in deformation, you called it.
Exactly. A change in the material's fabric, its texture at the crystal level. It's like taking that block of wood, it's still wood, but if you align the grain, sound travels through it differently. Same idea, but with rock under incredible forces.
So, okay, final question on this then. How do these crystals get aligned in solid rock? Is the mantle really flowing down there?
That is the key, isn't it? And the answer points to something geoscientists have suspected for a long time, but it's been hard to prove directly. It's a form of convection.
Convection, like boiling water.
Sort of, but much, much slower. This is solid-state convection. The solid rock in the lower mantle actually flows horizontally. Think incredibly slow, like centimeters per year.
Wow. Solid rock flowing.
It sounds weird, I know. Think of rock behaving like extremely thick, cold honey over millions and millions of years. Under constant heat and pressure, it can deform and flow.
And that flow lines up the crystals.
That's the idea. Murakami's experiments provide the first direct laboratory evidence that this slow, solid-state flow is happening, and that it's strong enough to cause this crystal alignment in post-perovskite.
So it confirms this suspected deep earth movement.
Yes, and that has huge implications. If we connect this to the bigger picture, it's not just solving the D array puzzle. As Murakami said, it opens a window into the dynamics and the depths of the Earth.
Right.
His quote was, "Our discovery shows that the Earth is not only active on the surface, but is also in motion deep inside. It really could be a turning point in how we understand our planet's engine. We're seeing the hidden dance within."
That is incredibly profound, because understanding these deep forces, that could ripple outwards, couldn't it?
Yeah.
Help us understand tectonics, volcanoes, maybe even the magnetic field shifts better.
Potentially, yes. It's all connected. What happens at the CMB in the D layer influences the mantle plumes that feed hotspots, affects the convection that drives plate tectonics.
Yeah.
It's all part of one big system. Understanding this deep flow is fundamental.
Yeah. And for anyone listening who wants to really dig into the details, the research paper is called "The Texture of the Post-Perovskite Phase Controls the Characteristics of the D Seismic Discontinuity." It just came out, May 23, 2025, in Communications, Earth, and Environment. What an amazing deep dive today. Seriously, from this strange seismic signal thousands of kilometers down to figuring out it's this subtle, powerful dance of crystals in flowing solid rock. It just shows how much more there is to learn right beneath our feet.
Absolutely. And this idea, this confirmation of solid rock flowing deep inside, it really challenges our basic intuition about the Earth, doesn't it? As this static ball of rock.
It really does.
It opens up all these new questions. How does this deep flow connect to surface events? What other slow, hidden movements are happening down there? It makes you think how much of our planet is constantly, subtly reshaping itself in ways we're only just starting to grasp. What else is waiting down there?
A truly mind-bending thought to end on. Thank you so much for guiding us through that today.
My pleasure.
And thank you all for joining us on the deep dive. Keep that curiosity going.